Exponents or powers tell you how many times a number is multiplied by itself. Hopefully you already know this. If not, well, then yikes. There are two parts. This part is referred to as the exponent, and this part is the base. Anything to the power of 0 is 1. There are many exponent laws that we learned in grade 10. We will briefly review them. When we multiply two powers with the same base, we can simplify the equation by adding the exponents. This works because if we write out the entire equation, it looks something like this. Next, if we divide two powers with the same base, we can subtract the exponents. This works in the same way as our multiplication rule. Similarly, if we have an exponent to an exponent, we can simplify by multiplying the exponents. If the powers are being added or subtracted, the only way we can simplify it is to factorize, as we are unable to combine the powers. Going back to our division rule, if we were to divide a to the power of 0 by a, we would get a negative exponent. A negative exponent can be simplified into the reciprocal of the power. For example, a to the power of negative 1 is equal to 1 over a, and similarly, a to the negative 2 is equal to 1 over a to the power of 2. We can generalize this idea into the formula a to the power of negative n is equal to 1 over a to the power of n. Exponents can also be fractions. Fractional exponents are the same as the nth root of the base. For example, 29 to the power of 1 over 3 is the same as the cube root of 29. A general statement for this is a to the power of m over n means the nth root of a to the power of m. Finally, if the bases are different but the exponents are the same, we can kind of factor out the exponent. For example, 2 to the power of 3 times 5 to the power of 3 becomes 2 times 5 to the power of 3. This can be generalized into the equation a to the power of n times b to the power of n is equal to a times b to the power of n. This also works for division. We can divide two expressions with the same exponent. There is a summary chart of all the rules of exponents on page 39 of our textbook. Exponential functions basically means a function with the variable in the exponent. The base of the variable exponent must be positive, as it is difficult to define exponents with negative bases as we cannot root a negative number. Basically, for exponential functions, when x has large positive values, y gets even bigger. Y will approach but never reach infinity. For large negative values of x, y values gets very, very small, close to, but never reaches 0. This is called an asymptote, as the line never touches the x-axis. For the graph y equals a to the power of x, the y-intercept is always at y equals 1 because anything to the power of 0 is 1. The entire graph is above the x-axis because a to the power of x is always positive for any value of x. The difference between a positive exponential and a negative exponential is whether a is greater than or less than 1. However, for negative exponentials, a cannot be below 0. Exponential growth and exponential decay are both calculated using this formula. This is used to model many patterns that are seen in real life. In this formula, n is the amount we are interested in, b is the initial value of n, a is the growth factor, k is the amount of time for one cycle of a, and t is the time that has passed. A great example of this is the half-life of radioactive materials in chemistry. The formula we learned in chemistry is NF equals Ni times 1/2 to the power of T over H. We have replaced many of the variables with different letters, but the nature of the formula is still the same. We now have NF instead of N and Ni instead of B. In this formula, half represents A, as the growth factor is always a half as signified by the name half-life. T still represents time, and H is the half-life of the material, which is the amount of time it takes for 1/2 of the material to decay. We can also add a C at the end if the background level that n approaches is not 0. C will be the background level, and B plus C is the initial n. This is useful for things such as the cooling of warm water to room temperature, where the value we are trying to reach is not 0 but room temperature. The number e is similar to 3.14 or pi and is simply a number we found that is present in nature. The number e is the constant 2.718. plus many more decimals that I do not want to read. Please now direct your attention to the board for an activity to better understand where this number comes from. Logarithms is an operation that reverses an exponent. It is used to find an unknown power. To explain, we will use the example 5 to the power of x is equal to 125. To find the unknown exponent x, we put the base of the exponent, in this case it's 5, into the base of the logs. We then multiply this by whatever the resulting power is. In this case, it's 125. This is our final equation. We then slap this into our calculator and we get the answer 3. A generalized formula for this is b is equal to a to the power of x, which is equal to log a of b. Many common logs have a shorthand. Log 10 is the default log, and we don't need to write the 10, and it will simply be log. Log e is simplified into in. Our textbook then gives us these following statements, and since the textbook doesn't bother to explain how they got these statements, I will do it for them. The first equation, log a of a to the power of x is equal to x, is simply derived from the equation a to the power of x is equal to a to the power of x, where we rearrange the equation by using our previous knowledge of logs. We move the base of one side into a log and get log a. Then we multiply that by the resulting power, which is a to the power of x, and all of that equals x. The second equation will be explained on the board as it is slightly more complicated. These relations are referred to as cancellation principles and can be used when simplifying logarithms. Lastly, this equation is similar to the equation explained on the board and follows the same principle, but we instead raise both sides to the power of x after. Basically, this equation shows how we can change the base of an exponential function to e. And remember, you cannot take the logarithm of a negative number or 0, as whenever you have a positive base, you cannot get a negative number. Many of the laws of logarithm are similar to the laws of exponents, and for the same reasons. The log of a product, two things multiplied, is the same as the sum of the logs. For example, log 2 of 45 is the same as log 2 of 9 plus log 2 of 5. The logarithm of a quotient, two things divided, is the same as the difference of the logs. We can use the previous example for multiplication to prove the division one too. Similar to how you multiply if there's an exponent of an exponent, the logarithm of an exponent is the same as multiplying the log and the exponent. For example, log 2 of 4 to the power of 2 is equal to 2 times log 2 of 4. The log of 1 is always equal to 0, no matter the base. Lastly, we will go through the change of base rule for logarithms. This is the formula. Once again, please direct your attention to the board for the explanation on why this formula works and where it comes from. Now we will do an example using this formula. To find the answer to log 3 of 25, we can use this formula to change the base. It then becomes log 3 of 25 equals log 10 of 25 over log 10 of 3. It doesn't matter which log you use as long as the log is the same in the numerator and the denominator. We just chose to use log 10 because it was the first thing that came to mind. Here are the graphs of 3 different logs. Due to the change of base rule we just mentioned, these curves all have the same general shape as they can all be rewritten as log x over something. There are some general trends we can observe from the graph of y equals log a of x. The graph will cross the x-axis at x equals 1 because log a of 1 is equal to 0. Similar to the exponential functions, log x is negative when x is less than 1 but greater than 0, and positive when x is greater than 1. The graph is also entirely on the right side of the y-axis as the log of a negative value is not a real number. The graph increases, so when x gets bigger, y gets bigger. And similar to how the x-axis is an asymptote to the curve in exponential functions, the y-axis is an asymptote to the logarithmic curves. Logarithms are frequently used in solving equations that contain the unknown in the exponent, as having the unknown as a factor makes it easier to work with. To find the solution to such problems, we first take the log of both sides of the equation. Then we can use algebraic laws to solve for the unknown. Example will be on the board. We can then use the laws of logarithms to simplify the answers as follow. You should know how to do this, but it is only necessary if the question specifies that you must do so. Some questions from 2G will simply require you to use the n equals b times a to the power of t over k formula. To solve these questions, we simply plug in the numbers and hope it works. We will do an example of these type of questions on the board. Here's a more complex equation involving using natural logarithms. For such problems, we can first take the natural logarithm from both sides of the equation and follow the laws of log to solve for the unknown. This last example will once again be on the board.